normal distributions. And what we want to work on is how do you use and interpret normal distributions. Later we'll go on and we'll build distributions. But the key thing is to look at what is a normal distribution, what's a normal curve, what is standard normal z-distribution, and what is a z-score. So these are things we're going to talk about. This is the vocabulary you're going to be working with. The type of problem I might solve with this is a problem of this nature. Those scientists have conducted aerial surveys of a seal sanctuary, and they can record the number of seals that they observe during each survey. So X is the number of seals they've observed each time. The numbers of the seals observed were normally distributed with a mean of 73 seals and a standard deviation of 14.1 seals. Find the probability that at most 50 seals were observed during a survey. At most 50 seals, which would be 50 or less. So we'll solve this problem at the end, but let's go ahead and get some background information. We've talked about probability distributions in previous sections, and one type of a probability distribution is what's called a normal distribution. So a normal distribution is modeled by the bell-shaped curve. So when people talk about grading on a curve, this is what we're talking about. They would fit grades into this kind of a curve based on the mean, which would be the average score, would be here in the middle, and the standard deviation. And the standard deviation is really sort of like the average difference from the mean. So it's a long, complicated calculation that we're not going to be doing in this chapter. But when you find the standard deviation, then you know that in a normal curve, there's a certain amount of data that lies within one standard deviation of the mean, and a larger amount of data that lies within two deviations of the mean, and a larger amount of the data that lies within three variations of the mean. So what those are, 68% of all the data lies within one standard deviation of the mean. So if you think of grading around a mean, you might find the average score on a test, and everything that lies within one standard deviation of the average you might make, let's say you made that a C, right? This could be a C. This is what we call grading on the curve. We don't grade on the curve in this institution. Grading on the curve forces you into success and failure by having you compete with each other, with the other students in the class, as opposed to showing how much you've mastered the material. So it's inherently flawed in terms of a method of assessing. 95% of the data lies within two standard deviations. So I might take this section here and say, okay, a second standard deviation above the mean is a B, but a second standard deviation below the mean is a D, and then everything below below two deviations would be failure, and everything above two deviations above would be an A. So this might be the way you set up grading. Okay, so 99.7 lies within three standard deviations of the mean. So what's way out here is very small. It's only 0.3%. So what you would say is 5% of people in this case would get either A's or F's. 68% would get a C, and then 13.5% would get a D, and 13.5% would get a B. That's sort of the way it would work. So that's grading on a curve. This is what the bell curve looks like. You see that within the sections that are within one standard deviation either way is 34%, 13.5%. This is 2.35%, and beyond three deviations is really a minuscule percentage, 0.15 on either end. Okay, it's symmetrical, and it's work based around the mean. Okay, so a normal curve is symmetrical around the mean. So if we want to look at using something like this, so a normal distribution has a mean of x bar. X bar means the mean, x with a bar over the top. That's the mean or the average. And a standard deviation, sigma, lowercase sigma. For a randomly selected x value from the distribution, find the probability, P is probability, that the item lies between the mean, that would be here, and two deviations. That would be here. Okay, so I would take this probability and this probability, 34% plus 13.5%, and that's going to be 47.5%. That's the probability that it's between the mean and 2 standard deviations below the mean. Okay, so go ahead and practice that for little do problems 3 and 4. It says 8.2, but it should be 8.6. I'm sorry. It says 8.2, but it should be 8.3. And then come on back. So here's another problem. Blood cholesterol readings for a group of women are normally distributed with a mean of 172. So that means here's my mean, and it's 172 milligrams per deciliter. This is the mean. And a standard deviation of 14 milligrams per deciliter. So if I add 14, I would get to this point. So that would be 186. If I add another 14, that would be 200. So now what I'm doing is I'm labeling this chart. If I subtract 1 standard deviation, that would be 158. And you can see now I can answer the first question. Between 158 and 186, that's from here to here. That's 34 plus 34, that's 68%. So 68%. Readings less than 158 are desirable. What percentage of the readings are desirable? So that's from here in this direction. That's 34 plus 13.5 plus, right, and you see 13.5, and this is 2.5. So that's 16. This whole set together would be 16%. 2.35, 0.15, 34 and 16. I'm sorry, not 34. We just want everything down below here. That's 16%. Right? Because we were talking about this area here. 16%. Okay, so another way to look at it is, you know, everything below the mean is 50%. So I could have, instead of adding these up, I could have taken 34 out of 50 and also gotten the 16. Both of those would have been completely correct. Okay, so go ahead and practice using that as well. Do problems 9 through 12. They all deal with one distribution. Answer those questions. Come on back to the lecture. We'll talk about it some more. So a standard normal distribution is a normal distribution with a mean of 0 and a standard deviation of 1. Now that doesn't happen very often. So you see that this is 0, -1, -2, -3, 1, 2, 3, right? So if you think back to the example we just did, that was not the case. And what happens is, in order for us to find this sort of scenario, the z-value for particular value is called a z-score. So this is the z-table, which is used for testing hypotheses. That's what it's used for. We're not actually going to get to that in this section, but it does have a purpose, and I think it's important to think about the purpose. So if you have a hypothesis, you would compare it to a z-score. The way I would calculate it from a population that would be one of my own creation as opposed to one that already fit into this board, I would take my actual value minus the mean and divide it by the standard deviation. So you can see if it was 1 less than the mean, then it would be 1 negative standard deviation divided by the standard deviation would give me -1. So that's how this happens, right? And in the study of statistics, you use z-values quite a bit for hypothesis testing. And so this is sort of getting you into the beginnings of understanding what is the z-score and where does it come from. And normally you pull z-values from tables as opposed to calculating them all the time. So what can happen is if z is randomly selected value from a standard normal distribution, I can use the table below to find the probability that z is less than or equal to some given value. Why do we have a table like this? That's because this only deals with z-values that are whole numbers. Well, what happens if my number is like right here? What happens if it's 0.4 and it's not 1? I need to know, right? I might want to know the probability that it's less than this. So if I come back over here and I go, oh, here's 0.4, I can find that probability. Okay, does that make sense to everybody? So I can use this table to find out that it's less than or equal to a specific value. So the table shows the probability is that z is less than or equal to negative 0.4, right? If negative 0.4 would be 0.3446. If it was positive, it would be 1 minus that, which would be 0.6554. So that helps us out a little bit. Okay, so this is normally where you would derive. You'd calculate your z value, then you'd pop into a table and you'd calculate the probability. Normally you can't read it off of a normal distribution like this because this only works when the z values are whole numbers, and they really just don't work out that way very often. So go ahead and practice deriving the z value from the table. Do problems 19 and 20. Come on back and we'll solve that problem about the seals. So here we go. We've got these seals, and you know what I'm going to do is I'm going to go back and I'm going to go ahead and snag that little image and put it on my slide here because it's helpful. It's easy to take the bell curve and then label it as opposed to trying to create it from scratch. Right, so I know that I have a mean of 73 seals, so 73 goes right here, and a standard deviation of 14.1. So I know that we're looking for, though, at most 50 seals, so I could go up. But the bottom line is those values are getting greater, so this would be, for instance, 87.1. If I go in the other direction, if I have 73 minus 14.1, it's going to be 0.9, and that will become a 2, and this will be 8. So this is 58.9, 58.9. At most 50 seals, so if I subtract another 14 out of this, that would be 44.7. So I know it's somewhere between 13.5 and 34, so I'm going to have to calculate my z value. So what we want to do is we want to take 50 minus 73, and then I want to divide it by the standard deviation of 14.1. So let's grab a calculator and do that. So 50 minus 73 is negative 23 divided by 14.1. So I get negative 1.6312. So we're going to round this to negative 1.6 and go back to our z table. So here's negative 1.6. So let's go ahead and look at that. Negative 1.6 right there. So this is 0.0548. Okay, so the answer would be 5.48%. Let's look on our table to see if that makes sense. We know it was somewhere around here. And we know that this is 2.5%, right, when I add these two and then a little bit more from this section here. So that makes sense, okay? So it's always good to keep sort of a logical sense in your head of, is my answer possible? Especially when you're pulling things from a table and you may feel like you don't quite fully understand what you're doing. So that's working with the z-score, and that's the end of this section.